Welcome back to the channel. In this new series, we'll be designing, analyzing, and optimizing a knuckle joint, a classic mechanical linkage used in tie rods, connecting rods, and tension members. In today's first episode, we'll focus on building the conceptual 3D model of the joint, setting the foundation for upcoming videos where we'll perform CAE analysis, optimize the design for performance, and make it ready for manufacturing. So let's begin by understanding the function and components of a knuckle joint. A knuckle joint is primarily used to connect two rods under tensile load. The joint allows a small amount of angular movement, making it ideal for mechanical linkages that experience slight misalignments during operation. Common applications include tie rods in engines, linkages in steering systems, suspension members, and structural connections in machines. The knuckle joint typically consists of three main parts: eye end, which connects to one rod; fork end, which connects to the other rod; knuckle pin, which joins both ends and allows rotation. To ensure safety and easy assembly, the pin is often secured with a collar and taper pin. Before we jump into modeling, let's define our concept design intent. We're not using exact standard dimensions yet. This model represents the conceptual geometry that we'll later refine through stress analysis and manufacturability checks. The goal here is to ensure proper proportions, clearances, and assembly fit between components. Let's begin our modeling with the fork end, which serves as the base connection for the knuckle joint. I start by creating two equispaced circular extrudes. These represent the fork arms in which the knuckle pin will be inserted. The spacing between these two arms is carefully maintained to ensure proper clearance for the eye end. Once the arms are ready, I connect them using a Y-shaped body, forming the main fork structure. This ensures strength and smooth load transfer between the arms and the shaft connection. After completing the fork head, I extend the design by creating the shaft portion, which connects the fork end to the main rod. Finally, I refine the geometry by adding fillets and chamfers at critical edges to make it more manufacturable and visually realistic. With this, our fork end geometry is complete. It now provides the correct interface and reference points for assembling the remaining components of the knuckle joint. Now that the fork end is ready, let's move on to the eye end, the second main component of our knuckle joint. I begin by sketching the rod axis and the circular eye profile at one end. The central hole in this eye will later accommodate the knuckle pin that connects it to the fork. After finalizing the sketch, I extrude the eye portion to the required thickness and then create the hole for the pin using a precise concentric constraint to ensure alignment with the fork geometry. Next, I extend the shaft portion from the eye body, maintaining the same center axis, so it can easily mate with the rod or link in the final assembly. Once the base geometry is complete, I add fillets and chamfers along the transitions to smooth out stress concentration areas and to give the model a more realistic, production-ready appearance. With this, our eye end is complete, perfectly sized to fit between the fork arms with adequate clearance for free movement around the pin. With the fork and eye ends ready, it's time to create the knuckle pin, the central connecting component that holds both parts together while allowing rotational movement. I begin by sketching the pin profile along its center axis. The main body of the pin is cylindrical, matching the whole diameter of the fork and eye. To restrict axial movement and improve strength, I add a collar on one side of the pin. This collar rests against the outer surface of the fork arm, ensuring the pin doesn't slide out during operation. On the opposite end, I prepare a small taper pinhole or locking slot, which will be used later to secure the pin in position during assembly. After finalizing the geometry, I revolve or extrude the sketch to form the 3D body and then apply fillets and chamfers on the edges for better aesthetics and to eliminate sharp corners. This completes the knuckle pin, which now precisely fits through the eye and fork holes, providing the pivotal connection for the joint. Now that all individual components, the fork end, eye end, and knuckle pin, are ready, let's assemble them to form the complete knuckle joint. I start by bringing all three components into the assembly environment and aligning them using the common center axis. First, I position the eye end between the two arms of the fork. Then, I insert the knuckle pin through the aligned holes of the fork and eye. I apply concentric and coincident constraints to ensure perfect alignment and fix the pin collar against the outer fork face, just as it would be in a real mechanical setup. Once the constraints are applied, I perform a motion check to verify the rotation of the eye end about the pin axis. This step confirms that the joint allows free angular movement, which is essential for its function in linkages and tie rods. Finally, I review the assembly in different orientations and create an exploded view, which helps visualize how each component fits and interacts with the others. With that, our concept knuckle joint assembly is complete, ready for further analysis and optimization in the upcoming parts. With the model completely assembled, it's time to perform an initial concept verification. I start by observing the joint in motion, rotating the eye end around the pin axis to ensure smooth articulation and proper clearance between the fork arms. This quick motion check confirms that the geometry is functionally valid and free from any interference. The exploded view helps us clearly visualize how each component, the fork, eye, and pin, come together to form a compact and robust linkage. At this stage, the design serves as a concept model, focusing on geometry and proportions. The next step will be to validate its performance under load. In the upcoming episode, we'll carry out a detailed CAE analysis to study stress distribution on the pin and fork, evaluate critical stress zones, and optimize the design for a better strength-to-weight ratio. This process will help us refine the model, ensuring that it's not just functional in 3D space but also efficient, durable, and ready for manufacturing considerations. This concludes the first part of our knuckle joint design and optimization series. In this video, we developed the concept model, from individual component creation to final assembly. The design is now ready for deeper evaluation and refinement. In the next episode, we'll move into the CAE stage, where we'll simulate real-world loading conditions to analyze stresses on the fork, eye, and pin. We'll identify weak zones, optimize the geometry for better performance, and prepare the model for manufacturing in later stages. If you found this video useful, make sure to like, share, and subscribe so you don't miss the upcoming parts of this series. Feel free to drop your suggestions or questions in the comments below. I'll be happy to discuss design improvements and analysis methods with you. Thanks for watching, and I'll see you in the next video, where we bring this knuckle joint concept to life through simulation and optimization.